A few people listed here, many of which are in the room. This work appeared in these two papers recently in the archive, and as you see from the title, I'll be exploring a little bit more the connection between Lyman limit system and the circumgalactic medium of galaxies. So by now we are all expert on absorption line systems. We're all expert on the circumgalactic medium. So I'll very briefly go through the introduction, and I will actually focus on a bit more quantitative analysis comparing numerical simulations and observations. And in doing that, I will highlight a couple of areas where we probably need to focus our attention and do a little bit more work. And towards the end of my talk, I will also propose an experiment to advance our understanding on how gas is distributed around galaxies. So let's get started. Very briefly, just to remind you why we care about Lyman limit systems in the context of understanding the circumgalactic medium of galaxies. I'm sure you have seen pictures like this many times now. This is a hydrodynamic simulation of a galaxy that is forming a redshift 3. The galaxy is here in the center, and as you are all aware, theory is predicting that this galaxy is being fed by cold gas in the form of these narrow filaments. What you're looking at here is a map of the total hydrogen. And so when you turn on the radiation field, ionizing radiation in the form of the UV background, or also ionizing radiation coming from stellar particles, what you see is that most of this gas is actually ionized. But you also see that there are pockets of gas that retain enough column density to become optically thick. And so this means that when you have a background source behind one of these galaxies, you should see some of these acritic gas as a Lyman limit system. So this is why we actually care about this population of absorber Lyman limit system when we study the circumgalactic medium. And so this is a fairly robust prediction of theory. It's not just in one or two models. There are several groups now that have performed similar analysis. And so a consistent finding is that some of this gas will show up in the form of optically thick hydrogen. And so let's explore a bit more what theory is telling us about how gas is distributed around galaxies, especially as a function of mass. So what we've done is to look at a fairly large sample when it comes to simulation. So we analyzed 21 galaxies. These are the high-resolution simulation of Daniel Severino, Avishai Dekel, Joel Primack, and collaborators. And what you're looking here is a subset of this sample. You're looking at maps of neutral hydrogen in blue, and the lighter blue is highlighting where the optically thick gas resides. Just to give you a reference for the scale, the virial radius is this circle. And for each galaxy, I'm also showing on the right the temperature map. And I'm sure you're all aware of this concept. We already heard a little bit about this in earlier talks today. When the halo grows in mass, we expect to see in between 10 to the 11, 10 to the 12 solar masses this sort of critical mass at which stable virial shocks form. And so the expectation from theory is that as we move towards higher halo masses, we should see less and less cold gas around galaxies. So I'm showing here exactly this quantity. This is the fraction of cold gas enclosed in the virial radius as a function of the virial mass for our sample. Open circle are galaxies redshift 3. Filled circles are the same galaxies as redshift 2. And so as you see, there is this decreasing trend. So the fraction of cold gas is decreasing as a function of halo mass. This has been seen before. But I would like to drive your attention to the fact that it's a little bit dangerous to extrapolate this plot to observable quantity. And so when it comes to actually understanding the distribution of optically thick hydrogen around this galaxy, we should actually be looking at a different phase. People typically look at cold gas as defined to be below a few times 10 to the 5 Kelvin. That's cold. But when it comes to neutral hydrogen, you actually want to look at the colder phase, at most a few times 10 to the 4 Kelvin, because about this temperature, electron collisions will start ionizing your medium. And so if you care about neutral hydrogen, you probably want to look at this phase. And as you see, this trend with halo mass is now mostly disappeared. And so there is a flat dependence with halo mass. We can also see this recast in terms of a more observable quantity. So we can look at what is called the covering fraction of optically thick gas. This is the area subtended by neutral hydrogen with Coulomb density above 10 to the 17 particles per centimeter square compared to a reference area that here we take to be the virial radius, the area defined by the virial radius. And so I'm showing this quantity as a function of the halo mass. And again, you see that there is no strong drop in the covering fraction as an halo grows from 10 to the 11, 10 to the 12. This is done at redshift greater than 2. And so please stop referring to the fact that when a halo grows in mass, there is a sudden drop in the covering fraction of optically thick gas at high redshift. So there is also a redshift effect. And so it's true that moving towards lower redshift, this accretion becomes less prominent, and so there are some redshift effects. But as far as the mass is concerned, what I can tell from this analysis is that there is no obvious difference between a halo at 10 to the 11 and a halo at 10 to the 12. The other point I would like you to take home from this plot is that there is quite a bit of scatter here. So if you look at the sample, you see there are halos that have a covering factor of a few percent. There are halos up to 25%, a bit higher redshift 3. It goes up to 30%. So the other point is we should probably start looking at samples of simulations when we want to compare to observation. It's a little bit dangerous to just pick one of these models and do our comparison. How does this compare to actual observations? This is shown here. This is the covering fraction as a function of halo mass, the same plot. Simulations are now down here. Again, open circle at redshift 3, fill circle at redshift 2. And I'm now adding some observed points to this plot. Here in green, you see the covering factor around Lyman bright galaxies. This is work done by Gwen Rudy and collaborators, Neil Crichton and collaborators. And so you see they infer a covering factor of about 30% or so. This seems to be slightly higher than what is captured in this numerical simulation. However, I would like to draw your attention to the 1 sigma error bar of this measurement. And so you see that samples are unfortunately too small at this point to say something very precise about how gas is distributed around galaxies in comparison to simulation. And I'll get to this point later. We already heard from Xavier this morning that there is actually a lot of cold gas around quasar-host galaxies. This is the analysis that Xavier showed earlier today. And so you see there is, as far as we can tell, quite a bit of difference compared to simulation. Joel already reminded us that there are physical effects that we should be taking into account, for instance, feedback. So this is certainly something that is going to help. However, I would like to emphasize that most of the current implementation of feedback in our numerical simulation will actually not really help to solve this problem. I showed you this map before. You see that the optically thick gas is mostly residing in this filament. And there is a very nice analysis by Zijin. I hope she'll say a bit more about this later today. Also, independent work by Frickman der Voort. What they did is to look at a very similar problem, but using SPH code. And so you can actually track the particles, and you can very nicely divide gas that is accreting versus gas that is outflowing. And so the punchline is it's true in the outflowing phase you have some cold gas, but the bulk of the cross-section is actually infalling. And so I think the problem here is to actually not increase the efficiency of feedback, but as far as I can tell, here we should really think how we can lift some cold gas, entrain cold gas within the hot phase. And so I hope there will be more discussion about this later today and tomorrow. Let's now go towards the end of my talk, and let me briefly touch upon what I just mentioned, which is when we look at Lyman bright galaxies, unfortunately, samples are too small to say something definite about comparing observations and simulation. The reason is that this is a very expensive measurement. What you want to do is you want to find pairs of quasars and galaxies. This is shown here and as an example. You see there is a bright quasar, so that's not hard to find. It's not hard to get a nice spectrum of it. What is actually hard is to do spectroscopic follow-up of all these little blobs here. And so when you want to find pairs of galaxies and quasars, you want to know the redshift of all the galaxies that start being very expensive, even for 10-meter telescopes. And so that's why we have samples of about 10 Lyman break galaxy quasar pairs. And so how can we progress? Of course, by investing more telescope time. We look forward also to the 30-meter telescopes. Meanwhile, I would like to show you with some numerical calculation that we can actually progress by looking at a more statistical quantity, which is the autocorrelation function of Lyman limit system measured against quasar pairs. Xavier already introduced the fact that we now know about a couple of hundred of quasar pairs from Sloan. Here is shown one of these pairs. And so let me briefly show how this idea works with some numerical calculation. So imagine to take a random patch of the universe. This is shown here. It's not very picturesque, but this is actually real in the sense that every single dot is representing the location of the halo in projection, as seen in a small region of the Bolshoi simulation. So this is capturing how structure formation, how according to cosmology, how galaxies are distributed. I'm sure you're all familiar with the concept of the autocorrelation function of dark matter halos. This is shown here, very trivial. I just want to emphasize that you are looking now at plots that are on a very small scale. And so I'm actually plotting distances that are relevant compared to the virial radius of a single halo. OK, so now imagine to have a bunch of quasars in your volume, and to use these quasars to probe the distribution of gas. This is the experiment I just described. And so let's take this quasar up here. The probability to find the Lyman limit system along the line of sight compared to this galaxy is clearly given by how the gas is distributed around this halo, just because the sideline is going through the virial radius of this galaxy. So nothing difficult here. Now if you consider a pair, a galaxy quasar pair, which is more widely separated, of course this quasar is not going to be intersecting that halo. But again, you can ask what's the probability to find a Lyman limit system? And that probability is going to be given by a joint probability of finding an halo, given that there is the halo you're looking at. And so this is given by the autocorrelation function of dark matter halos. And again, around that halo, you have a probability to intersect the Lyman limit system given by how much gas there is around that galaxy. And so, not surprisingly, when you do that measure in a cosmological box, you find these curves here. Every curve is for a different model for how gas is distributed around these halos. But the bottom line is at small separations, when you look galaxy and quasars that are separated by a distance that is comparable to the virial radius, you get the covering factor. While when you move to larger distances, you just recover the two-point correlation function for galaxies, and the normalization is again set by the covering factor. So far so good, but you might be wondering, well, you have been talking about galaxy quasar pair all the time, and so what's new? Why do we win in doing this? Here comes the trick. So suppose now you have quasar pairs in your box. And so let's forget completely about where the galaxies are. I'm not going to be asking that from now on. Now, suppose you have a quasar pair here, and you see a Lyman limit system around along the line of sight of the quasar. I'm going to be arguing that that statistically is telling you that there is a galaxy along the line of sight. And so if you look at the second sideline at close projected distance, that again is going to go through the halo of the same galaxy. And so by measuring the autocorrelation function of Lyman limit system, you'll be essentially probing the distribution of gas within the halo of that galaxy. You can do the same thing at large projected separation. One sideline is going to find the Lyman limit system down the line towards the observer. You can turn that into the second pair and ask, is there a Lyman limit system or not? And that quantity is going to bear some information on how gas is distributed around galaxy in the universe. Here is the result from numerical models. You see, I'm showing now with the red line the autocorrelation function of Lyman limit system. Again, there is no information on where the galaxies are. But again, you see that this is tracing very well the galaxy Lyman limit system correlation function. So this is, I think, I would argue, a very powerful tool to actually explore how hydrogen is distributed around galaxies and how galaxies that host optically thick system cluster in the universe. And so we should, I think, start measuring that. So if you see proposals, please be generous. I think I have maybe one more minute, and I'm not going to go into the details of this, but the idea is once we can establish clearly a connection between the population of Lyman-Limit system and the circumgalactic medium of galaxies, that's to be seen. But once we do that, I just want to drive your attention to the fact that people working on the IGM have been working very hard in the past few years to actually get nice samples, spectroscopic samples of quasars, and studying the property of Lyman-Limit system as a random intervening population along them. And so there are now several surveys led by people in the room, John O'Meara, Xavier Prochaska. We've recently completed a survey of Rashid 3 and Magellan. And so we have characterized from a statistical point of view the distribution of optically thick hydrogen in the universe fairly well. What you're seeing here is a quantity L of x, is describing the number of Lyman-Limit system you find as a function, you find per unit redshift as a function of redshift. And without going into the details for the aficionados of absorption line system, you can actually show that this quantity is related to how galaxies, or how optically thick gases distribute around galaxies. So if you're interested in this, come and talk to me. In the paper we show some models to describe this, but what I would like to do is to encourage people in the room that have larger cosmological boxes to actually go and start modeling this quantity. As you can see, this is fairly precisely characterized with observation, and so I would encourage you to go and look in your simulation and try to see what you get for this quantity as a function of redshift. And I think that is going to be a very powerful constraint to characterize the theoretical distribution of gas around galaxies. So if you're interested, please come and talk to me, and I'll just leave up my summary and take questions. Thank you.
Time for a couple of questions.
First, I want to know how the cell shielding correction has been done. This function that you used. The first part of the talk.
Okay, so what we do a full radial transfer modeling in post-processing. So we take this simulation, and then we generate packets of photon. It's a Monte Carlo code. Daniel Kesen has been involved in helping out with this. And so we follow the transport of photons until equilibrium is reached in the ionization condition, and we include both the effect of the UV background and local sources.
And then one more question is, when you show the correlation function, you seem to ignore the one halo term correlation function within the halo. Is that a problem or not? Or you intentionally ignored it?
So you're commenting on the exclusion effect?
Yeah, because you're looking at very close to the center, and below 1 megaparsec, the halo term starts to dominate the correlation function.
Yeah, no, that's I was trying to make that point as well. So you're absolutely right. When you look at this quantity, you have the 2-point correlation function out here. This is interesting, as you know. It's going to give you information on the mass scale for the halos that are also in Lyman-Limit system. And the 1 halo term is kicking in here, and that's the quantity we actually want to measure, because this is going to give you information on the covering factor of optically thick gas around galaxies. And also, in our models, it was fairly trivial. We just stick in a bubble of gas. But in reality, we expect a profile. We heard earlier today that this is certainly the case for magnesium 2. And so you can actually read that profile of the 1 halo term. I don't know if that's addressing your question.
I have a quick question, actually. So you have these streams feeding the galaxy, and you said that's where most of the optical depth is, at least below virial mass of about 10 to the 12. So is there any hope of getting spatial information? Because then maybe you will see this transition from below 10 to the 12 to above 10 to the 12, but only spatially rather than in an average sense.
I'm probably not understanding how that is going to be different, because when you have an average sense, you're essentially sampling the covering factor around halos. So probably I'm missing your question. Sorry.
Well, it's just it's a very small part of space where you're going to have a very high optical depth along that stream.
Yes.
And when you take an average, you lose that. And so you might see a greater difference with virial mass if you could actually really map the thing out spatially.
True, that would be terrific. So suppose you get a system with a bunch of background sources, Unfortunately, you cannot do that, and so you do a sort of composite experiment where you have a bunch of galaxy-quasar pairs, or in this case, quasar-quasar pairs, and so you have to essentially resort to a statistical approach. But again, even if the fraction covered is low, say like 10% or even less than that, I don't think it's less than that, but suppose 10%, you're going to recover 10 out of 100 sidelines. Will have an optically fixed system. So I think you are, as long as your sample is large enough, you're going to recover an even small covering factor.
Yeah. So do you have any idea where the most cross-section comes from? Is it from small halos or big halos, or which kind of halos?
That's a very interesting question. So these simulations live in somewhat limited boxes, or at least that's where we perform the analysis. So we sort of like cherry pick halos, and I haven't looked at the parent cosmological box. I very quickly look at the distribution or the cross-section around the satellites of these galaxies, and we find that when it comes to a bit larger column densities, so the DLA regime, so 10 to the 20 particle per centimeter squared and above, we find that is about half and half. So half of the cross-section is in satellite galaxies, and half is in the central galaxy. Yeah, I haven't looked specifically for the Lyman limit system.
Okay, let's thank Michele again.
Thank you.